Video 4 of Chapter 6. We are going to start a little series here within Chapter 6 focusing on binomial random variables. And we're going to get into some probability like we did back in Chapter 5, but these are very, very specific probability questions and they follow patterns. And we're not going to get to talk about the patterns in this video, but we will discuss the patterns that pop up in the next video. Now, first, we need to talk about what is a binomial random variable. And so if a scenario meets the following four conditions, then we're going to be able to call it a binomial distribution problem. So first off, if we call it a binomial problem, it's got to be binary, which means it's going to have two and only two outcomes. One of them is going to be considered a success, and the other we're going to call a failure. So I got some examples here. We have a baby boy versus a baby girl. You could call one of them a success and the other one a failure. Doesn't matter which one's which. Correct answer versus an incorrect answer. We may consider a success a correct answer, but in some cases, a success may be not getting a correct answer. It really depends on how we want to define that random variable. We could make a free throw or miss a free throw as a success or a failure. And maybe we have a big bowl of M&Ms and maybe we want to select a red M&M as a success. And if we don't get a red M&M, which could be a variety of different other colors, but if we were just going to say in general, a not red color would be considered a failure. So two outcomes. Next up, if the trials are independent, so that the result of one trial should have no impact on your future trials. So for instance, the same four situations involving kids, if you have a boy as your first child, that really shouldn't have any influence on whether your second child is a boy or a girl, and whether your third child is a boy or a girl. Same thing can apply with our multiple choice questions that we're either going to get right or wrong. Now, these multiple choice questions would have to be set up in such a way such that the answer to one question would not lead you to be able to answer the next question. So these are 10 completely separate, have nothing in common multiple choice questions. Your free throw attempts would have to be completely independent of each other. That if you made or missed the first shot should have no influence on whether you make or miss the second shot. That's a little bit of a stretch, right? Because let's say you make 18 shots in a row. Man, you are really going to be, I would think, nervous about that 19th free throw attempt. Maybe that's going to throw off your game a little bit. And maybe for some of you, you're like, no, I'm still going to make the same shot the way I made the last 18. So that one I would get maybe a little leery on. Are free throw attempts really independent? Maybe, maybe not. Now, I want to pick 40 M&Ms out of a bag. It should not matter. If I pick one red M&M, then the next M&M should not be influenced on whether that first M&M I picked was red or not. The third condition is we need a fixed number of trials. We're only going to do this binomial procedure so many times. So, for instance, if we're going to have 3 kids, you're only going to have 3 kids, and then you're going to stop. We're not going to have any more kids after 3. The multiple choice test, there's only 10 questions on this test. There's no more, no less. The free throws, we're only going to attempt 20, and this bag of M&Ms, it only has 40 M&Ms in it. So we're only going to do something so many times, and we call it a day. And the fourth condition is that the probability of success stays constant throughout each of our trials. So the probability is not going to shift. Now, one of the other conditions that we talked about, that the trials are independent, people will often kind of see the independent trials and the probability of success as really like one and the same. And in many cases, they are related to each other, that if the trials are independent, then the success shouldn't shift. So the one thing I would mention is an example of where independence and the probability of success as really not being the same thing. So imagine on a test, you have 10 multiple choice questions and 10 true-false questions. And each of those 20 questions altogether could be completely independent of each other. But the probability of success is not the same for all 20 questions. A multiple choice question, if it had, let's say, 5 choices on it, then you'd have an 80-20 probability of being able to successfully guess correctly, versus on a true-false question, it would be a 50-50. So there's a scenario where the probability of success is not constant, but the trials could be independent of each other. But again, I will say, for the most part, the independent trials and the probability of success, they will feel like they are directly connected. All right, so we can simplify our 4 conditions, and I've seen this acronym used, BINS, B-I-N-S, to represent our 4 conditions for a binomial situation. So B, binary, I, independent trials, N, number of trials are fixed, and S, the success probability is constant. So we're going to go through some examples and see, do these follow the 4 conditions to be considered a binomial problem? So a person holds up a playing card, and a friend guesses if it's red or black. The result is recorded, and that card is thrown out. The next card in the deck is held up, and the friend guesses again. This process is repeated 10 times. Let X equal the number of correct guesses. So option 1, are there 2 outcomes? Is there something we would consider a success and something a failure? And yeah, they're either going to guess correctly or they're not going to guess correctly. So green check mark, it is binary. Are the trials independent of each other? And I would say this is going to come out to be a no because of what they did with the cards. Once they recorded the result, they threw that card away, which means there's one less card in the deck. So that will influence on whether the next card is more or less likely to be red. So I would not say the trials are independent. So right now we could stop and say, overall, no, this is not a binomial type of problem. Now I want to keep going on though, because we can talk about these other things. Are there a fixed number of trials? Yes, we're only doing this with 10 cards. Is the success probability the same? And again, this is where it's really kind of connected with the independent trials. Once the first card is known if it's red or black, well then the next card will not have the same probability of being red, right? If the first card was red, now there's fewer red cards in the deck, so it's less likely the next card would also be red. So the probability of success is not constant. So again, overall, this situation is not a binomial distribution type of problem. Now, the next example, what if we were to roll a fair die 3 times and we record X, the number of 4s that we would see? So first off, is this a binary situation? And I would say yes. Now, some people would go, no, there's 6 numbers on a die. That's true, but we're interested in the number of 4s. We want to see 4s. And if we don't see a 4, then we're just going to say we didn't see a 4. Now, that could represent a lot of different numbers, right, on our die. But overall, yeah, there are 2 outcomes. There's 4s and there's not 4s. Do we have independent trials? And yeah, I would say our die, whatever we roll on their first roll, should not influence whether we see a 4 in the next roll more or less likely than the first roll. So our dice rolls are independent of each other. Are we only going to roll this die so many times? Yeah, only 3. Nope, try it again. There we go. And is the success probability the same for each roll? And yeah, every time we roll the die, that's a 6-sided die, we have a 1 in 6 chance of seeing a 4. And we have another 1 in 6 chance of seeing 4. And another 1 in 6 chance of seeing a 4 in those 3 rolls. So yes, this does meet the criteria of being a binomial distribution. So now we're going to continue on with this instance now that we found one. So to answer actual probability questions, we first need to determine the binomial probability distribution of X, the number of 4s. So first, let's consider all the values that X could be. So how many 4s could we see if we roll the die 3 times? Well, let's think of the minimum scenario. Let's say we roll 3 times. Do we have to see any 4s? And no, we could have rolled a 1, a 2, and a 3 on our 3 rolls. And so maybe at the minimum, we don't see any 4s. Now, we could see 1 4 pop up and the other 2 die rolls weren't 4s. Maybe we did see 2 4s out of our 3 rolls. Or you know what? Maybe, just maybe, we saw 3 4s out of the 3 rolls. So to create our probability distribution table, like we have been discussing this chapter and the previous chapter, X could represent 0, 1, 2, or 3 4s out of 3 rolls of a die. But now we need to work on these probabilities. Now, I mentioned earlier at the beginning of the video, these probabilities are going to follow a certain pattern, but it's not until the next video that we're really going to dive in and discover what that pattern is. So what I'm going to show you is what would happen if we don't know the pattern, and you guys don't know the pattern yet. So that's what we're going to discuss. How would we do this without a known pattern? And we have to go old school on this. So imagine we're going to make a tree diagram. Not a tree diagram. Yeah, a tree diagram. So let's say we roll that first die. And what are we going to see? A 4 or not a 4. And we roll the second die. And we're going to see a 4 or not a 4 based off the results of the first roll. And then the third roll, 4 not a 4, 4 not a 4, 4 not a 4, 4 not a 4. So now if we look at all of these end branch probabilities, here are all the different possibilities that could happen. And in the end, there are 1, 2, 3, 4, 5, 6, 7, 8 different possibilities that could happen. Now, if I wanted to come up with all the calculations, this is like what we did back in chapter 5. We get to multiply the branch probabilities along the way. So if we were to roll a 4, a 4, and a 4, each 4 had a 1 in 6 chance. So 1 in 6 times 1 in 6 times 1 in 6 would make 1 in 216. So let me put all of my calculations up here. There's 1 in 6, 1 in 6, 1 in 6. Rolling a 4 and not a 4, a 1 in 6, a 1 in 6, and a 5 in 6 for not rolling a 4. And then again, I have all of these various combinations of 1 in 6s and 5 in 6s. So that in the end, once I multiply all of those out, there are all of the probabilities of the 8 unique situations that could happen when I roll a die 3 times looking for 4s. So now we're going to take all of these probabilities and see where do they fit in my table. So first off, the 0 case. What is the probability of rolling no 4s? Well, if I look at all of my outcomes, there was only this one situation here in which we did not roll any 4s. And so that was the 125 out of 216, which comes out to be approximately 57.9%. So we move on. What's the probability of rolling 1 4? Well, when I look at my end branches here, there's 3 different possibilities of that happening. And that would be if the 4 happened on the first roll, the 4 happened on the second roll, or the 4 could happen on the third roll. And each one of those instances is a 25 in 216 chance. And so if the 4 could be on the first roll or the second roll or the third roll, I would add together those probabilities to get this 75 out of 216, which is 34.7%. So we move on to what's the probability of rolling 2 4s? Well, if I look back at my tree diagram, there are 3 instances of that happening. And that would be that the first 2 rolls were 4s, or the last 2 rolls were 4s, or the first and the last roll were the 4s. And each of those have a 5 in 216 chance. And when I add all them together, I get a 15 out of 216 chance, which is approximately 6.9%. And then last but not least, getting all 3 of my rolls to be 4s, that only happened one time in my tree diagram, and that probability was 1 in 216, which is approximately 0.4% of the time. That is not very likely. Now that we have this probability distribution table, we could answer probability questions like in chapter 5. Like, what's the probability of rolling exactly 2 4s? 15 out of 216, or 6.9%. Check. So easy. Move on. What's the probability of rolling at least 1 4? Ooh, at least 1. That means I could roll 1, or I could roll 2, or I could roll 3. So what would I do with those 3 probabilities? We would add them together. And what do those come out to be? That would add up to be, 42.1%. You're like, man, how did you do it? You must be really good at math. Well, yes, but I also looked at this probability, because this was the one event I did not want to see happen. So I subtracted this away from 1 or 100%, and I could do that math more easily in my head than adding these three probabilities together. So I did do some quick math, but not with these numbers. Now, what is the mean? Ooh, what is the mean of this? Ooh, well, that goes back to our earlier video from video 1. How do we find the mean of a discrete random variable? And if you remember, what we did is we took each value and we multiplied it by its probability. So it would look like this. We take the 0 times its probability plus, and remember we said we didn't have to do all 4 of them. We're just going to do ... and then do the 3 times the, now remember, if I do this as a decimal, this will be 0.004 for 0.4%. And then we could put, we could type all this in our calculator if we want. But remember, we used lists earlier. We said if we call this list 1 and this list 2, and we did our one variable stats. So going back to some review of video 1, this would come out to be, according to our calculator, and our calculator, it said X bar. And this came out to be approximately 0.497. Now, what if I told you that there's an easier way to calculate the mean, but of a binomial random variable? So what I'm about to reveal to you only applies if the situation follows a binomial distribution. And guess what? Great news. This is on the AP Stats exam formula sheet. So there is a very simple formula here that we can use to calculate the mean, again, only of a binomial random variable. This does not apply if it is not a binomial random variable. So N represents the number of trials. P represents the probability of success. All we have to do to get the mean is multiply those two numbers. So how many trials are we doing here? How many times are we rolling this die? 3 times. 3 times, that's right. What's the probability of success? What was the probability of rolling a successful 4? It was 1 in 6. So what is 3 times 1/6? Well, that would be 3/6, which is 1/2 or 0.5. So there's the mean. Now you might go, but we just calculated earlier that it was 0.497, and now you're telling me it's 0.5? But what I want you to realize is that was an approximate 0.497. These probabilities up here were not exact. They were rounded values. So if this was a question on the AP exam and this was a possibility of getting these two answers, you would get credit for either one. So really, these are really one and the same answers, even though they are very, very close. Now, what about the standard deviation? Oh, we could go old school. Right? We go old school video 1, be like, hey, what was that standard deviation formula? Oh man, there was a giant square root, and we had to take each value and subtract away the mean, which was, what would you say? It was half, right? 0.5. And we'd square that difference, and then we'd multiply it by its probability, and then we would do that for all of the values, and we get to the very last one, and we take 3, and we subtract away the mean, and we'd square that, and we multiply it by its probability, 0.004, and then we could put all this in the calculator again, do some one variable stats, and we would get the standard deviation. But again, Morpheus is here to save the day. There's a formula on the AP Stats exam formula sheet. We don't have to do the one variable stats again. Now you can if you want, but let me reveal to you this formula. So the formula is for the standard deviation, again, of only a binomial random variable. It is the square root of N, the number of trials, times P, the probability of success, times the complement of the probability of success, 1 minus the probability, which really represents the probability of a failure. So this is going to be the square root of 3 dice rolls times 1/6 probability of success times 1 minus a sixth, which is 5/6. And so what does that come out to be approximately? Let me do scanning brain memory functions, 0.6455, I think, if I did the math correctly in my head there. I also had the answer right down here. I just kind of saved that earlier, so I'm not Rain Man. But there's our standard deviation, 0.6455. And again, this is on the AP Stats formula sheet. Now, what I want you guys to do for the you do problem is, here's a new situation, and I want you to calculate the mean and the standard deviation. Just use the formulas. And I would say use the formulas because This is not an easy problem to do like how we did with the dice, with the tree diagram and coming up with all the probabilities, because we only rolled that die 3 times. And in this situation, you're doing something 100 times. So your tree diagram would be ginormous. Don't do the tree diagram. Don't do it. Don't even think about doing it. Just calculate the mean and standard deviation, and we will proceed on in the next video to talk about those special patterns in the probabilities, so we don't have to do the tree diagram every single time.